As you sit here, you are not stationary. You are spinning with the Earth at roughly 1,670 kilometers per hour. The Earth itself is hurtling around the Sun at 107,000 kilometers per hour. Our entire solar system is racing through the Milky Way galaxy at 828,000 kilometers per hour. And the Milky Way itself is barreling through the universe at roughly 2.1 million kilometers per hour. You feel none of it. Your coffee sits still in your cup. Your hair does not blow in any cosmic wind. And yet, you are moving right now at a combined velocity that would terrify you if you could feel it. But here is what should really stop you in your tracks. All of those speeds, every single one of them combined, do not even come close to 1% of the speed of light. Not even close. The speed of light is 299,792,458 meters per second. That is 1.08 billion kilometers per hour. Let that number breathe for a moment. 1.08 billion kilometers in a single hour. The fastest human-made object ever created, the Parker Solar Probe, reached a top speed of about 635,000 kilometers per hour, and engineers celebrated that as a monumental achievement. They should have. It is extraordinary. But that record-breaking speed is barely 0.00059% of the speed of light. Imagine a racetrack that stretches across the entire observable universe. The Parker Solar Probe, the fastest thing humanity has ever built, would not have made it past the starting line compared to a beam of light. Now here is where this gets personal. Here is where this stops being about physics and starts being about you, about your bones, your blood, your brain, the trillions of cells that keep you alive. The fastest a human being has ever travelled was during the Apollo 10 mission in 1969, when astronauts Thomas Stafford, John Young and Eugene Cernan hit a speed of 39,897 kilometers per hour on their return from the moon. That is the human speed record, and it has stood for over half a century. Light speed is approximately 27,000 times faster than that. 27,000 times. And yet even at that modest speed of Apollo 10, those astronauts were pushing against limits that the human body was never designed to handle. The human body evolved over millions of years for one very specific environment. A planet with 1 g of gravity, an atmosphere that maintains pressure on our skin, temperatures between roughly 0 and 40 degrees Celsius, and a maximum natural speed that, for most of our evolutionary history, was the sprint of a predator or the fall from a tree. That is what your body was built for. Your bones, your circulatory system, your nervous system, your cellular machinery, all of it was engineered by natural selection for a world where nothing moved faster than a cheetah at 120 kilometers per hour. And now we are going to talk about what would happen if you took that body, that fragile, beautiful, extraordinary collection of 37.2 trillion cells, and tried to push it to 1.08 billion kilometers per hour. This is not science fiction. Every single thing I am about to tell you is grounded in physics that has been tested, measured and confirmed through decades of experimentation. The effects of relativistic speed on matter are not theoretical. We observe them every single day in particle accelerators, in cosmic ray measurements, in the atomic clocks aboard GPS satellites that have to be corrected for time dilation, just so your phone can accurately tell you where the nearest coffee shop is. The science is settled. The question is simply this: what does that settled science tell us about the fate of a human body at the speed of light? The answer is more terrifying, more strange, more beautiful, and more profound than you might expect. And I need you to stay with me on this journey, because what starts as a question about speed ends as a question about the very nature of reality, time, consciousness, and what it means to exist. If you have ever wondered what it would really feel like to ride a beam of light, not in a movie, not in a cartoon, but in the cold hard reality of physics, then this is the most important conversation you will ever hear on this topic. And I promise you, by the end of this, you will never look at a beam of sunlight coming through your window the same way again. Let us begin with something that might surprise you. The danger does not start at light speed. The danger does not even start at half the speed of light or a quarter of it. The danger starts the moment you begin to accelerate, and it starts with a force so familiar that you experience it every single day without thinking about it. Gravity, or more precisely, the sensation of acceleration that mimics gravity. We call it G-force. You know what 1G feels like. You are feeling it right now. It is the normal pull of Earth's gravity on your body. It is what keeps you in your chair, what gives your coffee weight in your mug, what makes your heart work a little harder to pump blood up to your brain against the downward pull. 1G is home. It is comfort. It is normal. Now, if you have ever been on a roller coaster, you have felt maybe 3 to 4 Gs during the most intense moments. That sensation of being pressed into your seat, of your cheeks pulling down, of your vision narrowing slightly. That is 3G. Fighter pilots regularly experience 5 to 9 Gs during extreme maneuvers, and they wear special pressure suits called G-suits that squeeze their legs and abdomen to prevent blood from pooling away from their brains. Even with those suits, even with peak physical conditioning and specialized training, a pilot who sustains 9G for more than a few seconds will experience what is called G-lock, G-force, induced loss of consciousness. Their vision narrows to a tunnel, then goes grey, then goes black, and then they pass out. At 9G, the heart simply cannot pump blood to the brain against a force that makes your blood weigh 9 times its normal weight. Now here is the number that should make you pause. To accelerate from a standstill to the speed of light in 1 second would require approximately 30,600,000 G30 million Gs. That is not a typo. 30 million times the force of Earth's gravity, all at once, all pressing on every cell in your body simultaneously. To put that into perspective, the highest G-force a human has ever survived was 46.2 G, and that was Colonel John Stapp in 1954, strapped into a rocket sled on a test track in New Mexico. He survived, barely, but he suffered detached retinas, broken bones, and his body was bruised from head to toe from internal hemorrhaging. 46 Gs nearly killed one of the toughest test subjects in military history. We are talking about 30 million. At 30 million G, you would not die. You would not even have time to die. Every single structure in your body would fail simultaneously and catastrophically in a fraction of a millisecond. Your skeleton, which can withstand compressive forces of roughly 170 times its own weight before fracturing, would be crushed to powder. Your organs, which are suspended inside your body by connective tissues and ligaments, would be ripped from their moorings and slammed against whichever side of your body faced the direction of acceleration. Your brain, floating in cerebrospinal fluid inside your skull, would be compressed against the inside of your skull with a force that makes the worst traumatic brain injury in medical history look like a gentle tap. Every blood vessel in your body would rupture simultaneously. Every cell membrane would tear. The water inside your cells, which makes up about 60% of your body mass, would be driven by inertia in one direction while the dissolved proteins and minerals try to stay in place. You would not be a body anymore. You would be a compressed smear of biological material. But of course, nobody is proposing that we accelerate to light speed in 1 second. That is absurd. So let us be gentler. Let us be much, much gentler. Let us say we accelerate at a comfortable 1G, the same force you feel standing on Earth right now. At 1G of constant acceleration, you would feel perfectly normal. You could walk around, eat dinner, sleep in a bed. Your body would interpret the acceleration as simply being in a gravitational field identical to Earth's. It would feel like home. At 1G of constant acceleration, how long would it take to reach the speed of light? The answer is approximately 353 days, just under 1 year of constant, gentle, perfectly comfortable acceleration. That sounds wonderful, does it not? Almost too good to be true. And in a sense, it is, because while 1G acceleration would not crush your body, it introduces a different set of problems that are far more subtle and far more insidious. A year of sustained acceleration means a year of your body being under load. Astronauts on the International Space Station experience weightlessness, 0G, and even that causes severe physiological damage. They lose 1 to 2% of their bone density per month. Their muscles atrophy. Their cardiovascular system weakens because the heart does not have to work as hard without gravity. The fluid in their bodies redistributes, floating upward toward their heads, causing increased intracranial pressure that damages their vision. After 6 months in space, many astronauts require months of rehabilitation on Earth to walk normally again. Now, sustained 1G acceleration would actually prevent some of those problems because you would have a simulated gravitational force keeping your body under normal load. But here is what it would not prevent: the psychological toll of being sealed in a spacecraft for a year with no possibility of return. The radiation exposure, which I will get to shortly, and which begins to become dangerous well before you reach anywhere close to light speed. And perhaps most importantly, the fact that as your speed increases over that year, the relativistic effects begin to creep in, silently, invisibly at first, but building towards something that will fundamentally transform everything about your physical existence. Let us talk about what happens as you begin to pick up serious speed. Let us say you have been accelerating for several months and you have reached 10% of the speed of light. That is about 30,000 kilometers per second, or 108 million kilometers per hour. At this speed, you have already become the fastest human being who has ever existed by a factor of thousands. And at this speed, something is happening outside your spacecraft that you need to understand, because it is the beginning of a cascade of effects that will eventually become lethal. Space is not empty. I know it looks empty. I know we call it the vacuum of space. But it is not truly a vacuum. The interstellar medium, the space between stars, contains roughly 1 hydrogen atom per cubic centimetre. That does not sound like much. It is, in fact, an incredibly good vacuum by any earthly standard. The best vacuum chambers on Earth contain billions of molecules per cubic centimetre. Space has 1 lonely hydrogen atom. But here is what changes everything. Speed. When you are stationary relative to those hydrogen atoms, they are harmless. They drift around at thermal velocities, bumping into things with the energy of a gently tossed cotton ball. But when you are moving through them at 10% of the speed of light, the equation changes dramatically. Kinetic energy is proportional to the square of velocity, double your speed, and the energy of each impact quadruples. At 10% of the speed of light, each hydrogen atom that hits your spacecraft carries kinetic energy equivalent to a small bullet, and you are encountering millions of them per second across the cross-sectional area of your ship. It is like flying through a hail of microscopic bullets. Your spacecraft's hull is being sandblasted by individual atoms, each carrying more energy than a grain of sand fired from a rifle. At 10% of the speed of light, this is manageable with sufficient shielding. It is a problem, but it is an engineering problem. You can, in theory, design a shield thick enough and dense enough to absorb this bombardment. But as we keep accelerating, this problem does not just grow. It explodes. At 50% of the speed of light, each hydrogen atom impact carries roughly 25 times the energy it did at 10%. At 90%, the energies become comparable to those of cosmic rays, the most energetic natural particles in the universe. At 99% of the speed of light, each hydrogen atom hits with the energy of a fast-pitched baseball. A baseball. One single hydrogen atom, something so small that you would need to line up 10 million of them to span the width of a human hair, now carries the kinetic energy of a baseball thrown by a professional pitcher, and you are being hit by billions of them every second. This is not the kind of problem you can shield against with any known material. At these energies, hydrogen atoms do not just bounce off your hull, they penetrate it. They blast through metal like bullets through paper, and as they pass through, they create cascades of secondary particles, showers of radiation that multiply the damage. Every hydrogen atom that hits your shield creates a spray of neutrons, gamma rays, and subatomic debris that floods through the interior of your spacecraft. Your body is being irradiated by the very medium you are flying through, and there is nothing between you and it that can fully stop it. But the interstellar hydrogen is only one piece of the radiation puzzle, and frankly it is not even the most terrifying piece. Let me tell you about what the cosmic microwave background radiation does to you at near light speed, because this is one of the most extraordinary and horrifying consequences of relativistic travel that almost nobody talks about. The cosmic microwave background, or CMB, is the afterglow of the Big Bang. It fills the entire universe. It is everywhere, in every direction, with almost perfect uniformity. Right now, as you sit here, CMB photons are passing through your body. Billions of them every second, from every direction. And you feel absolutely nothing, because these photons have been stretched by the expansion of the universe over 13.8 billion years until they are now in the microwave part of the electromagnetic spectrum. With a temperature of just 2.725 Kelvin, which is about minus 270 degrees Celsius. They are among the lowest energy photons in the universe. They are completely harmless. But here is what Einstein's relativity tells us. When you move toward a source of light at high speed, the light you receive is blue-shifted. Its wavelength gets shorter, its frequency gets higher, its energy increases. This is the relativistic Doppler effect, and it is not a theoretical curiosity. It is a measured, confirmed, unavoidable consequence of motion through spacetime. At low speeds, this blue shift is negligible, but at relativistic speeds, it becomes dramatic. And what it does to the cosmic microwave background is genuinely terrifying. At 90% of the speed of light, the CMB photons coming at you from the direction you are travelling are blue shifted from microwaves into infrared radiation. You would feel warmth on the forward-facing side of your spacecraft. It would be like standing in front of a very gentle heat lamp. Uncomfortable perhaps, but not dangerous. At 99% of the speed of light, those same CMB photons are now blue shifted into visible light. The forward direction would glow. You would literally be able to see the cosmic microwave background with your naked eyes, something no human has ever done. It would appear as a bright, hot disk of light in front of you, blue, white, and intense. At 9% of the speed of light, the CMB ahead of you has been blue shifted into ultraviolet radiation. The forward side of your spacecraft is now being bathed in light far more intense than the surface of the sun. Without protection, your skin would burn in seconds. Your eyes would be damaged almost immediately. At 99.99% of the speed of light, the CMB has blue shifted into X-rays. The forward-facing wall of your spacecraft is now being bombarded with X-ray radiation, equivalent to standing in front of a medical X-ray machine that never turns off. Except it is not a narrow beam aimed at your broken arm. It is a wall of radiation hitting the entire forward hemisphere of your ship. The radiation dose at this point exceeds the lethal threshold for human beings within minutes. And at 99.999% of the speed of light and beyond, the cosmic microwave background, that gentle, harmless afterglow of creation itself, has been transformed into a barrage of hard gamma rays. The most penetrating, most damaging form of electromagnetic radiation that exists. Gamma rays that pass through metal shielding like it is not there. Gamma rays that shatter dinar molecules, that ionize atoms in your cells, that convert the peaceful glow of the ancient universe into a death beam aimed directly at your face. Think about that for a moment. The very light of the Big Bang, the oldest and most gentle radiation in the entire universe, becomes your executioner simply because you are moving too fast. There is a deep poetry in that. The universe is not hostile. It is not trying to kill you. It is simply that the rules of physics, rules that allow for beautiful things like stars and planets and life, those same rules make it so that moving too fast turns the universe itself into a weapon against you. Now I want you to hold all of that in your mind. The G-forces, the particle bombardment, the transformed cosmic radiation. Hold all of that, and let us talk about what is happening to the fabric of space-time itself around your body, because this is where things go from terrifying to genuinely mind-bending. In 1905, a 26-year-old patent clerk in Bern, Switzerland, published a paper that would fundamentally rewrite humanity's understanding of the universe. His name was Albert Einstein, and his theory of special relativity contained predictions so bizarre, so counterintuitive, so seemingly impossible that even many physicists initially dismissed them. But every single prediction has since been confirmed by experiment over and over with extraordinary precision. And two of those predictions are about to become very personal for you as you approach the speed of light. The first is time dilation. The faster you move through space, the slower you move through time. This is not a metaphor. This is not a philosophical statement. This is a measurable physical phenomenon. Time literally passes more slowly for objects in motion relative to objects at rest, and the effect increases as you approach the speed of light. At everyday speeds, the effect is so small that you would need atomic clocks to detect it, and indeed, that is exactly how it was first confirmed. In 1971, physicists Joseph Hafele and Richard Keating placed highly precise cesium atomic clocks on commercial aeroplanes and flew them around the world, once eastward and once westward. When they compared those clocks to identical clocks that had stayed on the ground, the clocks disagreed. The travelling clocks had ticked slightly differently than the stationary ones, by exactly the amount that Einstein's equations predicted. The difference was measured in nanoseconds, billionths of a second, but it was real and it was unambiguous. Time had passed at different rates for the travelling clocks and the stationary ones. Every single day, the GPS satellites orbiting Earth provide further proof. Those satellites carry atomic clocks that are critical for calculating your position, and those clocks tick 38 microseconds faster per day than identical clocks on Earth's surface, due to a combination of their speed and their position in Earth's gravitational field. If we did not correct for relativistic time dilation, your GPS would be off by about 10 kilometers per day. The fact that your phone can tell you your location to within a few meters is daily, practical, indisputable proof that Einstein was right. So what happens to time as you approach the speed of light? The mathematics are described by the Lorentz factor, usually written as the Greek letter gamma. At 50% of the speed of light, gamma is about 1.5. That means for every year that passes for you on your spacecraft, about 1.15 years pass on Earth. A 15% difference. Noticeable, but not dramatic. At 75% of the speed of light, gamma rises to about 1.5. Your 1 year is Earth's year and a half. At 87% of C, gamma reaches 2. Time for you now passes at half the rate it does for everyone back home. You experience 1 year, they experience 2. Still comprehensible. Still within the range of human intuition. But now the curve begins to steepen. At 90% of the speed of light, gamma is 2.29. At 95% it is 3.2. At 99% it is 7.09. For every year you experience, 7 years pass on Earth. Think about what that means. You leave Earth at 99% of the speed of light. You travel for what feels to you like 1 year. You turn around and come home. When you arrive, everyone you knew has aged 14 years. 7 for the outbound journey and 7 for the return. Your children have grown up. Your friends have aged. The world has changed. And you are only 2 years older. But we are not done. At 99.9% of the speed of light, gamma is 22.4. At 99% it is 70.7. At 99.999% it is 203.6. At 99.9999% it is 707.1. At that speed, you experience 1 year while 707 years pass on Earth. You could leave Earth, travel for a decade of your own time, and return to find that 7,000 years have passed. Every civilization that existed when you left would be ancient history. Languages would have changed, nations would have risen and fallen, and you would still be only 10 years older than when you left. And at the speed of light itself, at exactly c, gamma becomes infinite. Time dilation becomes total. From your frame of reference, if it were possible for you to reach the speed of light, time would stop completely. Not slow down. Not nearly stop. Stop. Completely and absolutely. Zero time would pass for you. The journey, no matter how far, would be instantaneous from your perspective. You could cross the entire observable universe, 93 billion light years from end to end, and it would take you exactly 0 seconds of your own time. You would depart and arrive at the same moment. For you, the departure and the arrival would be the same event. This is actually how photons experience the universe, or rather, how they would experience it if they had any capacity for experience. A photon emitted from a star in a distant galaxy, a photon that from our perspective travels for billions of years across the cosmos before striking the retina of an astronomer's eye. That photon from its own frame of reference existed for 0 time. Its emission and its absorption are, from its own perspective, the same event happening at the same moment in the same place. The photon does not experience the journey. There is no journey to experience. For a photon, the universe has no depth. Departure and arrival are one. Now consider what this means for your body. Your body is a time-dependent system. Everything about your biology runs on time. Your heart beats approximately once per second. Your neurons fire in milliseconds. Your cells divide over hours. Your hormones cycle over days. Your circadian rhythm runs on a roughly 24-hour clock. Every single process in your body is a clock, a sequence of events that unfold over time. If time stops, everything stops. Your heart does not beat. Your neurons do not fire. Your cells do not divide. No chemical reaction can proceed because chemical reactions require time. No thought can form because thoughts are sequences of neural events that unfold over duration. You would not be conscious. You would not be alive in any meaningful biological sense. And yet you would not be dead either, because death is itself a process that requires time, the progressive cessation of biological function, the decay of tissues, the dissolution of order into entropy. None of that can happen in 0 time. You would exist in a state for which we have no word, not alive, not dead, not frozen, because freezing is a physical process that happens over time. You would simply be a fixed arrangement of atoms, unchanging, unmoving through time, traversing the entire universe in a single timeless moment. It is the closest thing in real physics to the concept of eternity, and it is not the eternity of endless time. It is the eternity of no time at all. And this brings us to the second great relativistic effect on your body, one that is perhaps even stranger than time dilation, and that is length contraction. Just as your motion through space slows your motion through time, it also compresses your physical dimensions in the direction of travel. This is called Lorentz contraction. And like time dilation, it is not a trick of perception or measurement. It is a real physical compression of the spatial dimensions of moving objects. At 50% of the speed of light, your body, from the perspective of a stationary observer, would be compressed in the direction of travel by about 13%. If you are lying down in your spacecraft facing forward, and you are normally 180 centimeters tall, a stationary observer would measure you as about 156 centimeters. You would look slightly squished, as if someone had taken your image in a photo editor and compressed it along one axis. You would not feel this compression yourself, because from your own frame of reference, you are perfectly normal, and it is the universe outside that appears compressed. This is the strange reciprocity of relativity. Each observer sees the other as contracted. But as your speed increases, the contraction becomes extreme. At 90% of the speed of light, you would be compressed to about 44% of your normal length. That 180 centimeter body now measures about 79 centimeters to an outside observer. You would look like a caricature, a deeply distorted version of yourself, flattened as if pressed between two invisible plates. At 99% of C, you are compressed to just 14% of your normal length. You would be about 25 centimeters in the direction of travel, less than the length of a standard ruler. At 99.99% of C, you are down to 1.4%. That 180 centimeter body is now about 2.5 centimeters, roughly the width of a large coin, and at the speed of light itself, length contraction becomes total. Your dimension in the direction of travel becomes 0. You are infinitely thin. From the perspective of the universe, you have no depth at all. Now, physicists have debated for decades about whether length contraction is something that physically happens to an object, or whether it is purely a measurement effect, a consequence of the geometry of spacetime that does not correspond to any physical stress on the object. The consensus in modern physics is nuanced. In your own reference frame, you feel nothing. Your body is normal. Your organs are normal. Your cells are normal. But from the reference frame of the universe you are moving through, you are physically occupying a contracted region of space, and the electromagnetic forces that hold your atoms together, the quantum mechanical bonds that define the shape of your molecules, these are all participating in the contraction. It is not that you are being squeezed by some external force. It is that the very space you occupy has a different geometry at relativistic speeds. But here is where it gets truly interesting for your body. What if your acceleration were not perfectly uniform? What if, as is virtually certain in any real scenario, different parts of your body experienced slightly different velocities at the same moment? Your feet might be a fraction of a metre behind your head in the direction of travel, and that means, strictly speaking, they are at a slightly different velocity relative to the external reference frame during acceleration. The result is tidal forces, stretching and compressing forces that differ across the length of your body. At everyday speeds, these tidal forces are non-existent, but at relativistic speeds, with even slight variations in acceleration, they could become significant. Your body could experience differential contraction, where your feet are at a slightly different Lorentz factor than your head. The structural integrity of your spine, your connective tissues, your very cellular bonds would be tested by forces that no biological system has ever been subjected to. And there is another effect that ties length contraction and time dilation together in a way that should genuinely disturb you. If different parts of your body are at slightly different velocities, they are experiencing slightly different rates of time. Your feet might age at a fractionally different rate than your brain. The chemical reactions in your liver might proceed at a fractionally different pace than the chemical reactions in your heart. In your everyday life, this effect exists, but is so small that trillions of years would need to pass before you noticed a difference. But at near light speeds, with extreme Lorentz factors, even small velocity differentials across the length of your body could produce meaningful differences in the rate of time for different organs. Your body is a symphony of precisely coordinated biochemical processes, and that symphony depends on all the instruments playing at the same tempo. Differential time dilation within your own body would be like different sections of an orchestra playing the same piece at slightly different speeds. The result would be discord, biochemical chaos. Systems that depend on precise timing, like your heartbeat, your neural signaling, your hormonal regulation, could be thrown out of sync in ways that have never occurred in the history of biology. Let me take you now into something even deeper. Let us go beyond the physics of your body as a whole and down into the machinery of your cells, down to the molecular level, because this is where the story becomes almost surreal. Your body contains approximately 37.2 trillion cells. Each one is a microscopic city of staggering complexity. Inside each cell is a nucleus containing your DNA, roughly 2 meters of it coiled and folded into a space about 6 micrometers across. That DNA contains approximately 3.2 billion base pairs, the genetic code that makes you who you are. And that code is not just sitting there inertly. It is being constantly read, copied, repaired and maintained by an army of specialized molecular machines. Enzymes like DNA polymerase that replicate your genetic material with astonishing accuracy, correcting errors as they go. DNA repair enzymes that patrol the strands looking for damage and fixing it. Transcription factors that turn genes on and off in response to signals from elsewhere in the body. Your DNA is a living library that is constantly being accessed, and the integrity of that library is essential for your survival. Now remember the radiation we discussed earlier, the blue-shifted cosmic microwave background, the relativistic interstellar hydrogen. At near light speeds, your body is being pummeled by high-energy radiation from multiple sources simultaneously. And what does high-energy radiation do to DNA? It destroys it. A single gamma-ray photon can break both strands of the DNA double helix simultaneously, a so-called double-strand break. This is the most dangerous type of DNA damage because it is the hardest for your cellular repair machinery to fix. A single double-strand break, if not repaired correctly, can lead to a mutation. Multiple double-strand breaks can lead to cell death, or worse, to uncontrolled cell division. Cancer. Under normal conditions on Earth, your cells experience roughly 10 to 50 double-strand breaks per cell per day, mostly from natural background radiation and metabolic byproducts, and your repair machinery handles this beautifully. It is what it evolved to do, but at 99.99% of the speed of light, with the cosmic microwave background transformed into gamma rays and the interstellar medium hitting you like a particle beam, the rate of DNA damage would increase by orders of magnitude. Thousands, perhaps millions of double-strand breaks per cell per second. Your DNA repair enzymes cannot work that fast. No biological repair system can. The damage would accumulate faster than it could be fixed, and within minutes, perhaps seconds, the genetic code in every cell in your body would be shredded beyond any possibility of repair. Your cells would begin to die, not one by one, but all of them simultaneously as their operating instructions disintegrate. This is, in a sense, what happened to the victims of acute radiation exposure at Chernobyl and Hiroshima, but on a vastly accelerated timescale. The firefighters who responded to the Chernobyl reactor explosion in 1986 received radiation doses that destroyed their bone marrow, stripped the lining of their intestines, and caused their skin to slough off in sheets as the rapidly dividing cells in those tissues lost the ability to replicate. They died over days and weeks as their bodies fell apart at the cellular level. At near light speed, the radiation dose you would receive would make Chernobyl look like a dental X-ray. The cellular destruction would be almost instantaneous. But DNA damage is only part of the molecular catastrophe. Your body depends on proteins to function, and proteins are exquisitely sensitive structures. A protein is a long chain of amino acids that folds into a precise three-dimensional shape, and that shape determines its function. An enzyme that digests sugar has a shape that perfectly fits the sugar molecule, like a key in a lock. A hemoglobin molecule has a shape that allows it to grip an oxygen molecule and release it at precisely the right moment. The folding of proteins is driven by weak chemical forces, hydrogen bonds, van der Waals interactions, hydrophobic effects, and these weak forces are exactly what makes them vulnerable. High-energy radiation does not just break DNA. It ionizes atoms, strips electrons from molecules, creates free radicals, those highly reactive molecular fragments that rampage through cellular machinery like shrapnel. Free radicals can unravel proteins, breaking the weak bonds that hold them in their functional shapes. A denatured protein is a useless protein. An enzyme that has lost its shape cannot catalyze its reaction. A structural protein that has unraveled cannot maintain the architecture of the cell. At the radiation levels you would experience at near light speed, the proteins in your body would be denatured en masse. Enzymes would cease to function. Structural proteins would collapse. Cell membranes, which are delicate lipid bilayers studded with protein channels and receptors, would be torn apart as the lipids and proteins that compose them are damaged by ionizing radiation. The organized structure of your cells would dissolve into molecular chaos, and this would happen to all 37.2 trillion of your cells, more or less simultaneously. Think about what this means. You are not just a collection of chemicals. You are a fantastically organized collection of chemicals, and it is the organization that makes you alive. Every molecule in the right place, at the right time, in the right concentration, interacting with the right partners in the right sequence. Life is chemistry, but it is chemistry organized to a degree that borders on the miraculous. And what relativistic radiation does is destroy that organization. It does not just kill you, it erases the difference between you and a random mixture of organic chemicals with the same atomic composition. It is entropy, the tendency of organized systems to become disordered, delivered at the speed of light. Now I want to pull back from the molecular level and take you somewhere even more profound. I want to talk about your brain, your consciousness, your experience of being you, and what happens to all of that as you approach the speed of light. Because if you are interested in what light speed does to the human body, you are probably also interested in what it does to the human mind. Your brain is, by any measure, the most complex single object in the known universe. 100 billion neurons, each connected to up to 10,000 others, forming a network of roughly 1 quadrillion synaptic connections. A quadrillion. That is a 1 followed by 15 zeros. The number of possible states of that network is so large that mathematicians do not have a commonly used word for it. Your thoughts, your memories, your personality, your sense of self, all of it emerges from the electrochemical activity of this network. A single thought involves millions of neurons firing in coordinated patterns, sending electrical impulses down their axons at speeds of 1 to 100 meters per second, releasing neurotransmitter molecules across synaptic gaps that are only 20 nanometers wide, triggering cascading waves of activation that propagate across brain regions and give rise to, well, the experience of reading these words, the feeling of curiosity, the visual image of space in your mind's eye. All of it is neural activity, and all of it requires time. A single neural impulse takes about 1 to 5 milliseconds to cross a synapse. A complex thought, like understanding a sentence or imagining a scenario, involves sequential processing across multiple brain regions and takes roughly 300 to 500 milliseconds. Your conscious experience of the present moment is built from neural processes that unfold over a window of about 2 to 3 seconds. This is the temporal resolution of human consciousness. It is the speed at which you experience reality. Now, from your own perspective, travelling at near light speed, none of this changes. Inside your spacecraft, your brain functions normally. Your thoughts occur at the same speed they always do. You feel no different. This is the principle of relativity. The laws of physics, including the physics of neuroscience, are the same in all inertial reference frames. You cannot tell by any internal experiment that you are moving. But from the perspective of someone watching you from Earth, something extraordinary is happening. They see your time running slowly. At 99.9% of the speed of light, they would observe your neurons firing at roughly 1/22nd of their normal rate. A thought that takes you half a second would appear to take them 11 seconds. A conversation that feels to you like it lasts an hour would appear to them to last nearly a full day. And at 99.9999% of C, your brain activity, from their perspective, would be virtually frozen. A single thought would take hours of external time. A single heartbeat would take minutes. There is something almost paradoxical about this. From your perspective, you are thinking normally, experiencing time normally, living your life at a normal pace. But the universe outside your window is aging centuries while you form a single thought. Civilizations rise and fall in the time it takes you to blink. And yet for you, the blink takes exactly as long as it has always taken. Who is right? You, living your normal subjective life? Or the universe, watching you frozen like an insect in amber? The answer, according to Einstein, is that both are right. There is no absolute time. There is no master clock. Both perspectives are equally valid, and this is perhaps the most profound and disturbing insight in all of physics. But let me bring this back to the biology of your brain, because there is a question here that goes beyond physics and into the philosophy of mind, and it is a question we genuinely do not know the answer to. If your time slows to a near stop from the universe's perspective, and if, from your own perspective, everything feels normal, then what is the actual status of your consciousness? You would say you are conscious. You are thinking, feeling, experiencing, but an outside observer would say your brain is effectively frozen, that no information is being processed, that no neural computation is occurring. From their perspective, you are not conscious. You are a statue. Both perspectives are equally valid according to physics. This creates a genuine paradox for theories of consciousness. If consciousness is a product of information processing in the brain, and if from one valid reference frame that information processing has nearly stopped, then is the consciousness real or not? There is no consensus answer to this question. It touches the edge of what physics, neuroscience and philosophy can currently tell us. It is one of the genuinely open questions about what light-speed travel would mean, and it might be the most important question of all, because it asks whether you, the essential you, the experiencing self, would survive the journey even if your body somehow did. Now let us set aside the question of consciousness and return to hard physics, because there is something I have not yet told you, and it is arguably the most fundamental obstacle of all. It is the reason that everything I have described so far is, in the strictest sense, hypothetical. It is the reason that a human being reaching the speed of light is not just dangerous, but physically impossible. And understanding why it is impossible reveals something deep about the structure of the universe itself. You may have heard the statement that nothing can travel faster than light. This is true, but the way it is usually stated obscures the real reason why. It is not that there is some cosmic speed limit sign posted at 299,792,458 meters per second. It is not that there is a barrier you hit like a wall that prevents you from going faster. The real reason is far more fundamental. As you accelerate, your energy increases. That is intuitive. A faster car has more kinetic energy than a slower one, but in Einstein's framework, energy and mass are equivalent. E equals mc squared. Energy has mass, and mass has energy. So as you accelerate and your energy increases, your mass also increases. Not the mass you feel, not the mass that registers on a scale in your own reference frame, but the mass that the universe sees, the effective mass that determines how much additional energy is needed to accelerate you further. At low speeds, this effect is negligible. The mass increase when you drive your car from 0 to 100 kilometers per hour is so small that it would take the most sensitive instruments in the world to detect it, and even they probably could not. But as you approach the speed of light, the effect becomes dominant. At 90% of c, your effective mass is 2.29 times your rest mass. A 70-kilogram person now has an effective mass of about 160 kilograms. At 99% of c, your effective mass is 7 times your rest mass, about 490 kilograms. At 99.9%, it is 22.4 times, about 1,568 kilograms. At 99.99%, it is 70.7 times, about 4,950 kilograms, nearly 5 metric tons. You, a single human being, now have the effective mass of a large elephant, and at 999% of c, your effective mass is 707 times your rest mass, roughly 49,500 kilograms. 50 metric tons, the mass of a fully loaded semi-truck, all in one human body. And the curve does not level off, it accelerates upward toward infinity. As you approach the speed of light, each tiny increment of additional speed requires more and more energy because each increment adds more mass, which requires more energy, which adds more mass, in a feedback loop that spirals toward infinity. To reach the speed of light exactly would require infinite energy. Not a lot of energy. Not an unimaginably huge but finite amount of energy. Actually, mathematically, literally infinite energy. And since infinite energy does not exist in a finite universe, reaching the speed of light is not merely difficult, it is impossible. It is not an engineering problem that future technology might solve. It is a mathematical impossibility embedded in the structure of spacetime itself. This is worth pausing on because it tells us something profound about the nature of our universe. The speed of light is not just a speed. It is a fundamental constant of the universe, woven into the fabric of spacetime at the deepest level. It is the speed at which cause and effect propagate through the cosmos. It is the conversion factor between space and time in Einstein's equations. It appears in the equations of electromagnetism, of gravity, of quantum mechanics. It defines the boundary between what can cause what, between the past and the future, between events that can influence each other and events that cannot. The speed of light is the speed of causality itself. If you could exceed the speed of light, you could, in principle, travel backward in time. You could arrive at your destination before you left. You could witness effects before their causes. The entire structure of cause and effect, the structure that allows the universe to be predictable, that allows physics to work, that allows biology to function, that allows conscious minds to make sense of reality, all of it would collapse. The speed of light is not a prison wall. It is a load-bearing wall. Remove it and the entire edifice of physical reality comes down. And here is something beautiful and subtle that most people miss. The reason you cannot reach the speed of light is not a limitation imposed on you from outside. It is a consequence of your having mass. Anything that has mass, any particle, any atom, any molecule, any human body, cannot reach c. It is simply not a possible state for a massive object. Asking what would happen if a human travelled at the speed of light is, in the strictest physics sense, like asking what would happen if a triangle had 4 sides. It is not that it would be catastrophic, it is that the premise contains a contradiction. A massive object at the speed of light is not a thing that can exist in our universe, but here is what can exist. A massive object at 99.999999% of the speed of light. Incredibly close. So close that for all practical purposes the difference is negligible. And we do this every single day. At CERN, the Large Hadron Collider accelerates protons to 99.999991% of the speed of light. These protons are massive particles, just like you, just much, much smaller. They experience all the relativistic effects I have described. Their effective mass increases to about 7,454 times their rest mass. Their time runs about 7,454 times slower than ours. They are length contracted to a pancake shape. And they survive. They do not disintegrate. They do not vanish. They are simply very, very fast protons experiencing extreme relativistic effects. But protons are single particles. They are simple. They are bound together by the strong nuclear force, the most powerful force in the universe. A human body, by contrast, is 37.2 trillion cells held together by comparatively weak electromagnetic forces, chemical bonds, protein structures, and fluid dynamics. A proton can survive 99.999991% of C because it is fundamentally simple. A human body cannot, because it is fundamentally complex. Complexity is fragile. The more complex a system, the more ways it can be disrupted. And the human body is the most complex system we know of. Let me take you through something now that will tie all of this together. I want to walk you through the journey step by step, from the moment of launch to the theoretical approach of light speed. And I want you to feel what it would be like, as best as the physics allows us to reconstruct. You are lying in your spacecraft. The engines ignite. You feel a gentle push, like sinking into a slightly firm mattress. 1G. Exactly like standing on Earth. You could pour a glass of water and it would flow normally. You could toss a ball and it would arc normally. Everything feels utterly familiar. This is the beginning of a journey that will take you to the edge of physical reality, and it starts with a sensation no more exotic than getting out of bed in the morning. Days pass. Weeks. You are still at 1G, and your speed is climbing steadily. After 1 month, you are travelling at about 2.5 million kilometres per hour. After 2 months, 5 million. After 6 months, roughly 15 million. These are enormous speeds by human standards, far faster than any human has ever travelled, but they are still less than 2% of the speed of light. The relativistic effects are present, but so small that you could not detect them without incredibly precise instruments. Life on your spacecraft feels entirely normal, but outside your window, things are beginning to change. The stars ahead of you are very slightly bluer than they should be. The stars behind you are very slightly redder. The shift is too small for your eyes to notice, but your instruments pick it up. This is the relativistic Doppler effect, and it is the first visible sign that you are entering a new regime of physics. After about 100 days, you have reached roughly 3% of the speed of light. The interstellar hydrogen you are ploughing through is now hitting your forward shield with enough energy to produce detectable radiation. Your onboard radiation sensors have ticked upward. It is still well within safe limits, but the trend is clear and it is only going one direction. After 200 days, you're at about 6% of C. The blue shift of the stars ahead is now visible to the naked eye, if you know what to look for. Stars that should be yellow-white now have a distinctly blue tinge. Behind you, the stars are taking on a warm reddish hue. It is beautiful. You are seeing the Doppler effect in visible light, something no human eye has ever witnessed in a natural setting. After 300 days, about 10 months, you are approaching 10% of the speed of light, 30,000 kilometers per second, 108 million kilometers per hour. You are travelling so fast that if you aimed yourself at the sun from Earth, you would arrive in roughly 83 seconds. At this speed, the effects are becoming more significant. Time on your ship is running about 0, 5% slower than time on Earth. Not enough for you to feel, but enough that an atomic clock comparison would reveal a clear discrepancy. The radiation from the interstellar medium is now a genuine concern. Your shielding is handling it, but the dose rates are approaching the limits of what is considered safe for long-term exposure. And you still have most of the journey ahead of you. After 1 year, 365 days at 1G, you have reached approximately 77% of the speed of light. This is where the character of the journey fundamentally shifts. The Lorentz factor is now about 1.56. Time on your ship is running at about 64% the rate of time on Earth. For every hour you experience, about 1 hour and 34 minutes pass on Earth. Your length, from an external perspective, is contracted to about 64% of normal. The stars ahead of you are now strikingly blue. Some of them shifted into the ultraviolet and invisible to your eyes. The stars behind have reddened, and some have shifted into the infrared, disappearing from view entirely. Your forward field of view is dominated by an increasing brightness, and you have to dim the windows to avoid discomfort. The cosmic microwave background ahead of you has been blue shifted from microwaves into far infrared. You cannot see it, but your thermal sensors can. The forward wall of your spacecraft is detectably warmer than the aft wall, and the radiation from the interstellar medium has intensified dramatically. Your shielding is now absorbing significant energy, and the secondary radiation it produces is becoming a concern all on its own. If you continue accelerating at 1G, you will technically never reach the speed of light, but you will get asymptotically closer and closer. After about 2 years of ship time, you would be at about 97% of C. After 3 years, about 99.5%. After 5 years, about 99.99%. Each additional year of acceleration adds another decimal place of 9s to your velocity, but never quite reaches 100%. And with each additional 9, the relativistic effects intensify exponentially. Let me paint the picture at 99% of the speed of light. The Lorentz factor is 7.09. Your ship time runs at 1/7 the pace of Earth time. From an external perspective, you are compressed to about 14% of your normal length. Your effective mass is 7 times your rest mass. The stars ahead of you have been blue shifted so far that what was visible light is now ultraviolet and X-ray radiation. You cannot see stars ahead anymore in visible light. Instead, sources that were originally in the infrared or radio spectrum have been shifted up into visibility. The entire sky is distorted. Most of the light in the universe, from your perspective, appears to be coming from a bright circle directly ahead of you, the result of relativistic aberration, an effect that concentrates incoming light into a forward-facing cone. Behind you, the sky is nearly black. Almost no photons reach you from the rear, because they have been redshifted into radio waves too low energy for any detector to easily pick up. The cosmic microwave background ahead is now in the far ultraviolet. Your forward shielding is absorbing enormous energy and must radiate it away somehow, or it will melt. And the interstellar hydrogen hitting your forward shield is now depositing energy at a rate comparable to a continuous nuclear detonation. Each hydrogen atom strikes with the energy of a cosmic ray. Your shield is being eroded, ablated, destroyed atom by atom by the very medium you are travelling through. At 99.9% of C, everything I just described is 10 times worse. The radiation is 10 times more intense. The energy of each hydrogen impact is roughly 10 times greater. The time dilation is 22 times. Your length contraction is down to about 4.5%. From an external perspective, your 180 centimetre body is about 8 centimetres in the direction of travel. The forward hemisphere of your sky is now a blinding, searing disk of hard X-rays and soft gamma rays. Without shielding that does not yet exist and may not be possible, you would receive a lethal radiation dose in a fraction of a second. At 99.99% of C, the Lorentz factor is 70.7. Time dilation is 70 to 1. For every day you experience, nearly 200 days pass on Earth. Your length is contracted to 1.4%. That body is now about 2.5 centimetres. The cosmic microwave background ahead is now hard gamma radiation, the kind produced in nuclear explosions and the cause of collapsing stars. The interstellar medium is a particle beam of extraordinary intensity. Every atom in your forward path is a tiny bomb. Your shielding, whatever it might be, whatever impossible material science has conceived, is being destroyed. Not slowly. Quickly, the energy flux through your forward cross-section is now comparable to the surface of a star. If you were somehow still alive inside this spacecraft, you would not be for long. And at 99.9999% of the speed of light, we are in a realm so extreme that the numbers begin to lose intuitive meaning. The Lorentz factor is 707. Time dilation is 707 to 1. 1 year of your time equals 707 years on Earth. Your body, from an external perspective, is compressed to 0.14% of its normal length. That 180 centimetres is now about 0.25 centimetres, 2.5 millimetres, the width of a pencil lead. The cosmic microwave background ahead is now ultra-high energy gamma radiation, comparable to the most energetic particle beams physicists have ever created. The forward side of your spacecraft is receiving an energy flux that I can only describe as apocalyptic. No material, no shielding, no technology that obeys the known laws of physics could survive this environment for more than a few microseconds. If you were somehow, through some miracle of technology or magic, still alive inside this spacecraft and you were to look out the forward window, what would you see? Nothing recognizable. The human eye responds to electromagnetic radiation with wavelengths between roughly 380 and 700 nanometers. At 99.99999% of C, all the visible light in the universe has been shifted, in the forward direction, to wavelengths thousands of times shorter into the extreme gamma-ray part of the spectrum. And sources that were originally in the radio spectrum have been shifted up into the visible range. What you would see, if your eyes could somehow function in this environment, which they emphatically could not, would be a universe completely unlike anything human eyes have ever perceived. Patterns of radiation that correspond to radio sources in the actual universe, radio galaxies, pulsars, molecular clouds, all rendered in visible light and concentrated into a tiny, intense dot directly in front of you. Behind you, near perfect blackness. To the sides, a thin ring of distorted multicoloured light, sometimes called the starbow, where the full spectrum of Doppler shifting plays out in a ring around your direction of travel. But of course, your eyes would not function. Your retinas are delicate layers of photoreceptor cells, rods and cones, each one a biological photodetector exquisitely tuned to respond to visible light photons. Gamma-ray photons would not trigger these receptors. They would destroy them. A single gamma-ray photon carries enough energy to ionize thousands of atoms, and your retinas contain some of the most radiation-sensitive cells in your body. Your vision would not blur, it would not fade, it would be obliterated at the cellular level before your brain could register a single frame. And your brain. Your beautiful, magnificent brain with its 100 billion neurons and quadrillion synapses, even if everything else somehow held together, your brain would be destroyed by radiation in seconds at these speeds. Neurons are among the most metabolically active cells in the body, and they are among the most vulnerable to radiation damage. They do not divide in adulthood, which means that unlike skin cells or blood cells, they cannot be replaced. A neuron destroyed by radiation is gone forever. And at the radiation levels present at 99.9999% of C, neurons would be destroyed en masse, their delicate membrane potentials disrupted by ionizing radiation, their synaptic machinery dismantled, their axons and dendrites shattered,